quantum mechanics, I mean, people say it's a most wonderful theory and most amazing description of the universe. Yes, that's true. It is a wonderful theory, and it gives you an amazing description of the universe, but it doesn't give you a description of the universe which involves significant mass displacements. That is to say, a massive body in two places at once. You're only looking at things where the mass of the bodies can be ignored. And all experiments to the moment which confirm quantum mechanics involve effects where the mass displacements are much too small to have any effect. So you want to have an experiment where you're beginning to see this effect. And this was telling us where, you see, quantum mechanics has this problem that it gives you ridiculous answers if you think of it for macroscopic bodies. I mean, why couldn't a rock sitting on the table here be in these two places at once? And according to the framework of quantum mechanics, sure, they could be in two places at once. But you never see a rock in two places at once. And that depends upon going a little further, and you have to say, well, if you consider the gravitational field of the rock, and can that be consistent with quantum mechanics? You lead into certain problems. And these problems seem to indicate that lifetime of a rock being in two places at once, that's a finite lifetime. And for an actual rock, it would be a ridiculously tiny fraction of a second. If you try and put it in this place and this place at the same time, it wouldn't last, would be absolutely instantaneous. It'd become one or the other. And that's what we would experience in actual life. We don't see things in superpositions of two places at once. I mean, people often say, well, the reason you don't is because the environment has got involved in the thing. That's that's not a real answer. You have to say, why does the environment actually make a difference? And if you go into the calculations, you look at it, no, it doesn't answer the question. It's because the environment is also, it's sort of moved around, yes, and the environment can be most of the movement in the system. And that's why the thing can't be in two places at once, because the environment has been jiggled too much. But there's no experiment yet that has looked at this effect of why quantum mechanics, if you like, gets into trouble with macroscopic bodies. And when you have mass displacements, well, you see, it's a long way from the experiment that has been done, that Yvette was just describing, the one where you have the bodies in free fall and compare it with the one on the table, so to speak, and you see this T-cube factor. That's just the first hint of why macroscopic bodies don't behave as you might expect as a quantum mechanical system. And it's the first little clue. That's why it's important. And I think that it's only a little clue, but it's important as being the first little clue, as far as I can see.
So it sounds to me like this Ron Fullman T-cubed experiment is testing whether the equivalence principle holds in quantum mechanics. Okay, seems like the answer is yes. It seems to me like it would be more interesting if the answer was no, because that would indicate there's some inconsistency there. And it sounds like what you're saying, Roger, is that Yvette's experiment takes this further to test a collapse model, a certain type of collapse model, namely yours.
Okay, so let me clarify a few things and talk about the experiments that are taking place by other groups, and so to put the whole thing in context. I mean, the reason why Roger says that Ron is experiment is very far away is because effectively the experiment of Ron is with one atom. And maybe it's good to also make the distinguish between passive gravity and active gravity that you usually make. And I think this sort of clarifies things. So you have the Earth active mass, let's say, makes the atoms fall. And then you would say, okay, but then the Earth has a passive mass, but the sun has the active mass that makes the Earth move around. No, so that was I think it was given by Newton, this distinction. No, so what Ron has is that he has the atom as a passive mass in a superposition in the active mass of the active gravitational field of the Earth, but the field the mass of the system itself is just in superposition in the presence of the field of the Earth. And what Roger calculations and ideas and so sort of he argued is that under that circumstance, the equivalence principle and the superposition principle they're not in conflict with each other. No, so that's exactly what Ron shows, and what Roger was just explaining now, just put in active, passive terms, is that when you have now, forget about the Earth. There's no Earth. It's just the superposition of the atom with itself. So in that case, it's the active mass of the atom in a superposition that Roger pointed out that in that case, there is a conflict between the equivalence principle and the superposition principle that should lead to the collapse. Now, why in the experiment by Ron you cannot measure that is because for one atom, the effect is tiny. So you would have to wait, I think it's 10 to the 20 seconds or something like this to see the effect for one atom. So basically you can just neglect that and forget about it. But the point is that when you start having heavier systems, then this becomes relevant. So Roger and I wrote a paper where we were exploring the possibilities of doing an experiment with a Bose-Einstein condensate. And in that paper, we gave numbers. So usually this atom interferometry experiment, that's a good reference that we were talking about for Ron. The experiment, it takes milliseconds. That's how long he can hold this superposition. You would need, let's say, if Ron could keep a superposition for a second or two, which is still really far away from what experiments done, but it's not impossible. But in order to see the effects of self-gravity, you would need something like 10 to the 9 atoms in a superposition. So a mass, like for example, could be a lump or like a silicia bead with the equivalence of like, let's say, very roughly speaking, with 10 to the 9 atoms in it. And that's very different to the one atom that Ron had, and his experiment is impressive, but tests something different. Now, there has been progress in testing the superposition with massive systems, and like I mentioned before, the record is currently by Markus Arndt at the University of Vienna, where he puts these molecules that have like 2,000 atoms each. Well, but that's the molecule in superposition with itself. But that's the comparison with, I think now he managed to do this with an order of magnitude more, but I don't know. I heard, so I don't know if that's like published yet or not.
Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind-the-scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, CurtJaimungal.org.
But last thing I heard was that he managed to take it one order of magnitude further. So let's say something like 2 times 10 to the 4. Compared to we found 4 times 10 to the 9, really far away.
Yes.
And it's very difficult to take those steps by making things more and more precise. And there's many groups around the world working in that direction. Ron Foldman himself, he wants to do the experiment with diamonds, which have a lot more mass. But it's very difficult to put solids in a superposition because they're very hot. So they can, for example, Marcus can cool down the molecules to I think it's microkelvin temperatures. And those temperatures are still too hot to see the gravitational effects. But still, there's a lot of activity worldwide because of the importance of this experiment to our understanding of the interplay of quantum mechanics and gravity, that there's many people trying. So they use nanodiamonds, silicia beads, silicia rods, membranes, cantilevers. There's a number of possibilities. But if you see, all of these involved solids, and that's kind of the state of the art and where things are at, no? So now a Bose-Einstein condensate, we were talking about that before. You can cool down to half a nanokelvin. So from millikelvin to half a nanokelvin, that's like a really long, and then you would say, well, why? No, that was kind of the idea. Why not use a Bose-Einstein condensate? So they have another problem. Maybe before I go into Bose-Einstein condensate, I would also like to mention work from two other people that I'm like impressed.
Sure.
And another one is Marcus Aspenmeyer, who is also at the University of Vienna. So I spent 3 years there because of these amazing people, because I like to propose experiments and so on. So having the opportunity to talk to the two Marcuses, Anton Seilinger is also there. It's just an amazing place to do experiments. Marcus Aspenmeyer can cool down a bead to quantum scales, and these beads are pretty big. They have like 10 to the 8 atoms. So they have kind of getting the mass right, but he hasn't been able to put the bead in a superposition. So he can cool this big system to the ground state, to quantum scales of a harmonic oscillator, but he's still working towards doing the superposition. And another person that I would like to mention is Hendrik Ulbrich, who's at the University of Southampton.
Okay.
And he's done some really beautiful experiments measuring gravity with these nanobeads. So these are like the smallest sort of systems that they can still measure gravity between two different, not just one, it's like two different systems. It's not quantum yet, but it's really like their technology is really getting quite impressive. But still very far away from being able to test if gravity collapses the wave function. So we wrote this paper on what could you do with a Bose-Einstein condensate, because could we use as an advantage that you can cool it down to those temperatures. But now, here comes the big problem, is that if you take a Bose-Einstein condensate, what you want to do to test gravity is that you want to create a superposition of the atoms left and right. Actually, I didn't say what a Bose-Einstein condensate is. Maybe I should start there. So take an atom in a well and cool it down to the ground state. So that you do in second year quantum mechanics is the typical example. And it's really beautiful because what you see when you cool down the atom to the ground state is that it becomes completely delocalized in the potential. So it's not just like left or right, it's like everywhere. Now take 10 to the 5. That's like the typical size of a Bose-Einstein condensate for most experiments. 10 to the 5, 10 to the 6, rubidium, sodium, something like this, atoms into the ground state. So the system, because atoms are bosons, the system behaves like a big macroscopic system behaving quantum mechanically. So that's very nice, and people use them for many things. But now the challenge is take the 10 to the 6 to we need 10 to the 9 actually, to create a superposition of left and right. And that is very difficult because a Bose-Einstein condensate is not a solid, it's a fluid. So in particular, the atoms are not bounded together. And the moment that you lose one single atom from this superposition, all of them left, plus all of them down, that left and right. So you would do this in what we call a double well potential. So people in the lab have already done these double well potentials. Like, for example, Marcus Overthaler in Heisenberg. Several people, but I remember him in particular, that you can have these atoms in these double wells, but nobody has been able to do a superposition of left plus right in that way, because if you lose one, the whole thing collapses. And actually, they just haven't. I think the record is 2 atoms or something like this by Chris Westbrook in this situation. So, whereas the temperatures seem to be kind of promising, well, then the fact that the atoms, if you lose one, is so fragile, then again made the possibility look very unlikely. But then, what people actually do in the lab is that they don't prepare these states, which are actually called noon states, because are n on the left, nothing on the right, plus nothing on the right, n on the left, so they're called noon states, is that they've been able to prepare another type of states that are very interesting. So in a double well potential, again, because the atoms are not bounded, you can have the atoms tunnel from one well to the other. Now, the Nobel Prize a few days ago, on the 7th of October,
right,
was given to tunneling. In a different system, right? But the fact that atoms can tunnel through a potential. So what you have in a Bose-Einstein condensate is that in a double potential is that the atoms can tunnel from one well to another. And that gives you like a variety of quantum states that you cannot get in a solid. Because in a solid, they're all bounded together, so you can only do a superposition here. But in a double well, you could do more like a whole family of very rich quantum states. One type are called like 2-mode squeeze states. And this is like superpositions of 1, 1, 2, 2, 3, 3. Like a more sophisticated states. But some of these generalized states have already been produced in the lab with quite a few number of particles. So those are accessible to the experiment. So then you would say, why don't you test gravitational effects, active gravity, in those systems that people have already produced that sort of states? Well, because there was no formalism to study the gravitational self-energy for that kind of states. And actually, well, we tried for a while, but now I have developed like a new formalism that allows you to study self-gravity for these new states. And then you can use these easier, more accessible states that don't have the super strong requirement that you would have on one hand on solids, or on the other hand on the new states, to test the gravitational effects. And this is the experiment that Roger sometimes mentions. And I think I should say that the experiment, I'm a theoretician. You know, I figured out how to calculate the self-gravity for this state and proposed the experiment. But the experiment is been done by Philippe Boyer at the University of Amsterdam and Chris Westbrook, who's in Paris. So is the team are, you know, us, and with the advice always of Roger. And of course, we have students and so on. So it's a very nice team. I love it. I love working with Philippe and Chris, and of course with Roger. And well, let's see if this alternative route gives us some results, hopefully in the near future.
Roger, why is this T-cube test? Why is it with Ron Follman? Why is it causing such a hubbub in the physics community among the people who know about it?
I'm a bit confused myself, so I don't think I can answer your question. I think I get the impression that Ron was not quite so. I mean, what I regard as important about his experiment, he was not regarding perhaps as the main feature of the experiment. I'm not sure.
I don't think so. I think Ron is very much in agreement with the importance.
Well, I was a bit puzzled because he was trying to remove the term principle of equivalence from his he was suggesting, I mean, he's changed his mind. I said, that's ridiculous, you see.
Yeah.
So he seemed to have a somewhat different view about the importance of his experiment.
Yeah.
I don't know. Maybe I've got it wrong.
No, I don't think so. I do think that he sees it in the same light as you do. I think there's been some confusion about it because the point that Roger makes is a subtle one. It's a subtle point, and I think not always is that maybe people working in atom interferometry and quantum experiments are not that familiar with the subtleties of it, and somehow I think it goes somehow overlooked. That's why I think it's great that Roger explains his point of view and so on in this alternative
go
way.
along with it. I mean, he wasn't removing the principle of equivalence, but I just thought the fact that he was puzzled me. That's all.
Yeah.
But it seems to me it's an important experiment, and it ought to be. I mean, it's not unexpected in the sense that when you look at the subtleties of the principle of equivalence in connection with quantum mechanics, we don't.
But that's the case, like with every proposal. Like you propose something, right? That you prove mathematically using the theory. Like what example that I gave about, I took the theory of Berry phase and then put a vacuum state, and and then for me it was like, well, the fact that this was shown was not a surprise, because the mathematics and the theory showed already. I don't know very well why there was a controversy about it. Sometimes there's a controversy on like the assumptions that you might make in a given proposal or in a different result. But in that way, an experiment confirming like a theory, sometimes they say, oh, well, it was not expected. But it's always like, in a way, a surprise, because the theory can have places where it goes wrong, right? Like well, I mean, hopefully not in the mathematics, but sometimes, or more likely, I think, in the assumptions made. So it's always, for me, a big thing when an experiment confirms a piece of theory.
The Economist covers math, physics, philosophy, and AI in a manner that shows how different countries perceive developments and how they impact markets. They recently published a piece on China's new neutrino detector. They cover extending life via mitochondrial transplants, creating an entirely new field of medicine. But it's also not just science. They analyze culture, they analyze finance, economics, business, international affairs across every region. I'm particularly liking their new Insider feature. It was just launched this month. It gives me a front row access to The Economist's internal editorial debates, where senior editors argue through the news with world leaders and policymakers in twice weekly long format shows. Basically, an extremely high-quality podcast. Whether it's scientific innovation or shifting global politics, The Economist provides comprehensive coverage beyond headlines. As a TOE listener, you get a special discount. Head over to economist.com/TOE to subscribe. That's economist.com/TOE for your discount.